800 million years after the Big Bang, the James Webb Space Telescope caught a single point of light, the size of our entire solar system. It looked like a star. But when astronomers ran the numbers, the math broke. This object was pouring out 100 billion times more energy than any known star can produce. Not brighter, not larger, 100 billion times beyond what nuclear fusion allows. For years, Webb had been finding hundreds of these small, blood-red points scattered across the infant universe. Objects nobody could classify. Astronomers called them little red dots, and quietly admitted they had no explanation. Then, in August 2026, one of them stopped hiding. They gave it a name: MOM-BH-star-1. What they found inside that light doesn't just explain one anomaly. It suggests something far larger has been hiding in the dark since the beginning of time, and we've been looking straight through it. Since 2022, the James Webb Space Telescope has been staring into the deepest reaches of the visible universe. And again, it kept finding the same strange signature. Tiny red points of light, packed with far more energy than they should hold, sitting at distances that placed them just a few 100 million years after the Big Bang. Astronomers gave them a name: little red dots. Half affectionate, half a confession that no one knew what they were looking at. Nothing about them added up. If they were young galaxies, they were far too compact, crammed into a space that should be teeming with newborn stars, not collapsed into a single blinding point. If they were quasars, the blazing disks that surround growing supermassive black holes, the light was wrong. Quasars have a signature: hot, blue. These dots glowed red, as if buried under dust that shouldn't exist this early in cosmic history, or hiding something behind that dust alone couldn't explain. The candidates piled up, hundreds of them. The papers piled up too. But consensus? Zero. Some researchers argued they were young, chaotic galaxies forming stars at the absolute limit of what's physically possible. Others suspected something darker, a population of black holes growing faster than physics allows, wrapped in gas so thick it disguised them as something else entirely. The debate went nowhere because no single object was clean enough to test. Every dot's light was tangled with the galaxy around it, its true nature buried under noise no algorithm could fully strip away. Astronomers needed exactly one thing. One object, isolated enough, bright enough, to show what was hiding inside, with nothing in the way. In the summer of 2026, they found it, and it turned out to be almost impossibly clean. Clean enough that what came out of it would end up rewriting the question entirely. That impossibly clean signal was about to do more than confuse a few astronomers. It was about to rewrite the question entirely, starting with where it came from. In the primer survey, which Webb ran over a patch of sky called UDS, one object stood out from the rest. It was fainter than its neighbors in one narrow wavelength range, and brighter than everything around it in another. A combination so specific that a team led by astronomer Rohan Naidu locked onto it. Webb's spectrograph stayed fixed on the object for more than 4 hours, breaking its light apart wavelength by wavelength. The result? A redshift of 7.7569. Translated into time, That's just 660 million years after the Big Bang, about 5% of the universe's current age. At that distance, the object stays unresolved. No structure, no spiral arms, no disk, no galaxy shape at all. Just a single point, modeled at a size stretching tens of astronomical units across, comparable, edge to edge, to the size of our entire solar system. And out of that point came an amount of energy, with no honest explanation in stellar physics. 100 billion times more than any star could ever produce through nuclear fusion. Not a bright star, not a supergiant. A physical impossibility, hiding inside a single unresolved point of light from a universe that had barely cooled down after its own birth. Naidu's team checked the obvious explanation first. Could this be a dense cluster of young stars faking the signal? The spectrum answered clearly. No. Could it be a measurement error, an artifact of distance and dust? They checked that too. It didn't hold up. Whatever MOM-BH-star-1 actually was, it didn't behave like anything already on the books. And what Naidu's team proposed next was so strange, it almost didn't sound real. The team's answer was almost too theatrical to publish with a straight face. A black hole wearing the mask of a star. Picture a young, rapidly growing black hole, roughly 100,000 times the mass of our sun, wrapped inside a colossal, dense shell of hydrogen. Not a disk. Not the jets you usually see drawn around black holes. A cocoon. Matter doesn't just orbit a black hole like this. It plunges straight into it, spiraling down, heating as it falls, radiating that infall energy outward through the surrounding gas until the whole structure glows like a star that fusion never actually powered. Astronomers coined a name built for exactly this contradiction: a black hole star. And when Naidu's team took the clean, unblended spectrum of this object and mathematically laid it over the light of an ordinary young galaxy, something clicked into place the way it never had before. The resulting signal reproduced, almost perfectly, the pattern seen across hundreds of unexplained little red dots. One clean sample may have just revealed what's hiding inside all the rest. But that's where the comfort ends. A black hole this massive should not exist this early in the universe's life. Current growth models cap the rate, feed too fast, and radiation pressure is supposed to choke the growth, throttle it, regulate itself. This one didn't slow down. Something let it grow faster than current physics allows. And nobody in the paper published in Nature claims to know what. A separate 2026 survey has already found 241 candidates that look just like it. 241 objects that simply shouldn't have had the time to form. If even a fraction of those 241 candidates hold up, the story of the early universe won't need a correction. It will need to be rewritten from scratch. Every model of supermassive black hole formation leans on a fixed amount of time. First, small black holes, then centuries of slow, physics-obedient growth, and only after that, monsters a billion solar masses strong, the kind that anchor galaxies today, including our own. MOM-BH-star-. One skips the slow part entirely. It hints that some black holes were born already massive, or found a hidden mechanism to grow at a rate the equations call impossible, and did it while the universe was younger than the length of a human childhood. nobody has an answer for how. The discovery team itself is careful, almost restrained in its wording, calling their calculations simple, idealized, a first approximation, not proof, not the final word. But the team's caution only extends to the math. There's a question they phrase much more quietly, and it's far more dangerous to the whole picture than the growth rate of one black hole. If objects like this really existed in batches just 660 million years after the Big Bang, and if even some of them kept growing at that same rule-breaking pace, then where did they go over the next 13 billion years? What does a black hole star become once the hydrogen cocoon finally falls away? The answer to that question might be closer to home than it first appears.
The answer to that question might be closer to home than it first appears. Astronomers have long wrestled with a separate, equally stubborn puzzle. Quasars found within the universe's first billion years already carry black holes weighing billions of solar masses, masses that, by standard models, should take far longer to build than these objects ever had. For years, researchers called it the too big, too early problem, and no one had a real answer. Mom BH Star 1 and its 241 possible relatives are the first time astronomers have had more than a hint. A working candidate for the missing link, a black hole star growing inside its hydrogen cocoon, breaking every speed limit physics allows. Exactly the kind of bridge that was missing between the first small black holes and the fully grown monsters inside ancient quasars. If the mechanism found in one point of light in the UDS field operated everywhere in the early universe, it might not be an exception. It might be the normal way almost every supermassive black hole we see today was born, including the one sitting at the very center of our own Milky Way, Sagittarius. A star, a black hole over 4 million times the mass of our Sun, the one our entire galaxy orbits, also had to start somewhere. The standard story assumes a slow climb stretched across billions of years. But if the rules found inside MOM-BH-star-1 aren't an anomaly, if they're a forgotten chapter in the history of every black hole like it, then somewhere in the universe's first billion years, at the future center of our own galaxy, there may have been its own star that shouldn't exist. Invisible, hidden inside a cocoon of light we will never be able to see directly. The Discovery team calls their numbers a first approximation. The 2026 survey calls its 241 objects only candidates. But if even one of them ever confirms the same link found in UDS, this stops being a question about a distant point of light at the edge of the observable universe. It becomes a question about what made us, and we still don't know the answer. If you don't want to miss the next candidate when it's found, subscribe so these stories don't pass you by.